here we are then. Paper 6, this one is the second in the pack that you've been given. The 62 here. So let's get cracking. I suppose that before I get started, I suppose the one thing I would say with this one, I found the first half to be more challenging than the second. You may have been different to me, but I think it really does emphasise the point, which I can't stress enough, is that you do need to just spend 45 minutes on each cut off. Ensure you are dedicating the allocated 45 minutes to the second half of the paper, and hopefully there's some time to go back and check over, add some more marks if you can. So let's turn the page and get started. Right. First up, the mean of 6 positive integers, 4.5. Calculate the sum of those 6 integers. Well, this is sort of question that we tend to fire at you when we're doing mean, to work the other way. So the sum of them had to be 6 times 4.5. If you think about undoing it, which gives us 27, and we're off to a flyer. Okay, now we've got here, just reading this through, it's all about consecutive integers added together. Complete this table for the sequence of 2 or more, and they are again consecutive positive integers. So it's important that these sequences are all consecutive numbers, and you can see here when we have a little look at them, they are all consecutive. Okay, so with the 6 of them, well, we could just add these up, couldn't we? And then divide by 6 to find out this mean. When we do that, we get 7.5. And the sum of all the terms, well, I can just add them up, 45. There's going to be some sort of link between them, but at this stage I don't really know what that is. The next one, well, we've been given the 31 terms. We've given the mean of 25. Well, what's the sum of them got to be? Again, I could, I suppose, go through 10 plus 11 plus 12 up to 40 if I'm unsure of what to do at this stage. But hopefully we're spotting it's the same as the first question. We have the mean and we have the number of positive integers. So we're going to do 25 times 31 to give us 775. Okay. Next one, the number of terms, well, we can count them, 1, 2, 3, 4, 5, 6, 7. The mean we can work out quite easily. Well, and actually, hopefully we're seeing a bit of symmetry. It's going to be bang in the middle, isn't it? So actually, if I look at this, it's going to be that 5 there. Again, I could put in the numbers and divide by 7. And just a little check, 7 times 5 is 35. So I'm confident in my answer there. Next, we've now got less information in this one. We know the sum of the terms is 42. We know the number of terms is 4. Well, actually, to find out the mean then, it's going to just be 42 divided by 4. That's how we always do it. Comes up with 10.5. And we know there's 4 terms. I know 10.5. Now, the thing that I'm picking up from this is the idea of this mean. This mean is bang in the middle of the sequence. 25 you can't see, but 5 you can see is bang in the middle, and so 10.5 is going to have to be bang in the middle of the 4. So that means I would start writing this out as, well, the 10 and the 11, and then clearly I need to have a 12 above and a 9 below, and there's the sequence. Okay, final column then. The sum of the terms is 49. Now, there's all sorts of things that could be happening here. My instincts are to try and see how many terms there could be in this sequence. Now, it says here that it has to be 2 or more, so I would try 2. It seems that if it is possible, then it would be the easiest way of doing it. So it's a 2 here, perhaps with a question mark. I'm going to see if it would work. If it does work, then the mean would be 24.5, simply doing 49 divided by 2. And again, setting up in the same way as I did in the previous row here, then it would be a 24 and a 25. And it looks to me like that works. So let's just rub out the question mark. Oh, no, that's not rubbing it out. We're Okay, and now we can move on to part B. Describe how to calculate the mean using only the first term and the last term of the sequence of the consecutive integers. Also, let's have a look at what the link is between them. We've got a 5 and a 10, and this 7.5. We've got a 10 and a 40, 25, a 2 and an 8, which gives us 5. Hopefully there's enough information here already to see that the link is, if we added these two together, then it would divide by 2, it would give us this mean, which works well with what I was saying, with it hitting the midpoint. 10 and 40 added together is 50, divided by 2 gives us 25. So I'm just going to write that out here. So I need to write something like add them and divide by 2. Okay, let's move on. Part 3. So more algebraic now. We've got k plus 1, k plus 2. So it's consecutive integers again in a sequence. Write down the number of terms in this sequence. Well, what I'd do for this is I would see k as being my first one, k plus 1 is my second, k plus 2 is my third, which says to me that whatever this number is, the number of term is one more, because obviously this effectively has a 0. So k plus 99 would have 100 terms. Okay, use the first and last term to find expression for the mean. Okay, so we need to do the same as we did before. So the first plus the last divided by 2. So that is just k plus 99 over 2, or 2k plus 99 divided by 2. Part C then, use your answer in part A and part B to write an expression for the sum of all the terms in the sequence. Okay, so let's have a look. We've got the number of terms here, which is 100. We've got the mean, which is this, and we said right at the start that we could do mean times the number of integers to give us the sum. So we just need to multiply them. So let's just do this. I'm going to do 100 times 2k plus 99. I tell you what, I'll put the entire thing in the bracket. That's probably better. Divided by 2, which I can simplify a bit. If I'm multiplying by 100 and dividing by 2, that's the same as multiplying by 50. So that would be 50, 2k plus 99. And then if I expand my bracket, I'm going to get 100k. And 99 times 50 is 4950. Okay, moving on, question 4. Use a method of question 3 to show that the sum of the integers k plus 1 up to the final value, which is now no longer 99 but it's n minus 1, and that's what we said, it was the number of terms minus 1. That's why this was 100 minus 1 to give us the 99, is this. Right, so we're going to have to use exactly the same process, but instead of my k plus 99, I've now got k plus n minus 1. So I'm just thinking here, can I pick up on some of my communication marks? So my mean is what I'm going to write first. My mean, which is k plus n minus 1. And that's divided by 2. My number of terms, well, that is n. And what I'm actually going to do is multiply them. So it's n times 2k plus n minus 1 over 2. And we've arrived at what we wanted to. QED. Okay, next page. If n is odd, explain why the value to the expression 2k plus n minus 1 must be an integer. Okay, so if n is odd, well, I'm just looking within this expression. if n is odd, 2k must be even because it's multiplied by 2. Anything multiplied by 2 is even. So what we've got is we've got an even plus an odd take away 1. So an even plus, well, an odd take away 1 must be even. What's happening is I'm then dividing that by 2, so it's going to be an even divided by 2, so it's a whole number. So in mine, I've put, if n is odd, then 2k plus n minus 1 must be even. So then, when you divide by 2, gives an integer answer. Part B then, if n is even, explain why it must end in 0.5. Right, so similar process. If n is even, let's think about what the denominator is going to be. 2k an even plus another even, take away 1 must be odd. Then when divided by 2 gives an integer answer. Okay, now this next question is the point at which that I just made me think a little bit more, got a little bit uncertain, took a bit of time, had to kind of grapple with it quite a bit. So this is the point in time where I'm going to say to you, don't get caught up in it. Keep an eye on the time, okay? Remember, you're looking for 45 minutes. Now, if you've got to this point and you do get stuck here, hopefully what you've achieved already is, hang on a second, 5, 6, 8, 9, 10, 14 marks, potentially 15 out of the 20. So you're better off ensuring that you pick up the marks in the second section rather than just getting stuck at this point. But let's go through what I did anyway. Obviously, I've still got a bit of time before my 45 minutes is up, so I can spend a bit of time just trying to get to the bottom of this one. So part 6, the sum of the sequence of consecutive positive integers is 84. Using question 4 and question 5, find all the possible values for n and the corresponding values for the mean. So let's just write down some of this information. The sum is 84, which means n times 2k plus n minus 1 over 2 is equal to 84. And that's the thing that I was dealing with in question 5 and was given to us. So if I try and manipulate this a bit, I get n times 2k plus n minus 1 would be equal to 168. And let's manipulate this slightly. We've got 2k would have to equal 168 over n, take away n plus 1. Okay, let's just give it a little bit of context and think about what k is and what n is. N is the number of terms, so that's one of the things that I'm trying to establish and work out. Now, in order for it to give a, sorry, just lost myself from the question, all values of n and the corresponding values for the mean. The question is, in terms of the context, what does k represent? Well, let's just go back a second and look where k first came into play. K here is the first number in the sequence. If k is the first number in the sequence, it has to be an integer. Okay, so we can't get k to be 0.5 or anything else, so k must be an integer. So if I look at what's the expression that I've just kind of made here, if k has to be an integer, then we need to think about the ideas of odds and evens, just like we did in part 5. So now you imagine inputting a value into this, and then what we need to do is we need to divide by 2 at the end, which means if I'm dividing by 2 at the end to work out what k is going to have to be, then this whole thing would have to be an even number in order for k to then be a whole number. Yeah, this has to be an even number in order for that when you divide it by 2, then it's going to be a whole number for k. So what I suggest we do at this point is we try some numbers and see some numbers for n that would work. Now I'm going to just think about factors of 168. So wouldn't hurt for me to write out the prime factors just to know. So my factors, oh, wrong one. No, right, a bit more space, there we are. So my factors of 168, what I'm going to do is write down the prime factors because my GDC can give me those. And it tells me that 168 is equal to 2 cubed times 3 times 7. I'm just going to simplify my process a little bit. Obviously multiples of them, different combinations of those multiplied together are going to give me the factors. So let's try first of all n equals 2. So that's all we're doing. We're going through a process of trying different numbers out. And the first one I want to try is n equals 2. So if n equals 2, let's see what happens. Well, I'm looking back at this now. Okay. I'm looking back at this now, and we're going to go, forgot to press record, 168 divided by 2, take away 2, oh, it's off the screen, isn't it? Plus 1. So the question is, does that give me an even or an odd number? Well, 168 divided by 2 is 84, take away 2 is 82, plus 1. 84. '83 divided by 2. Just lost some of my mental arithmetic there, but it's going to give me. So this thing is 2k equals, and it would be 2k equals 83. So therefore k equals 83 over 2, which is not an integer. So therefore n cannot equal 2. So we need to go through this process for other potential factors. Looking at my prime factors, obviously 2 is an option, 3, the next one, is an option as well. So let's try it. So if n equals 3, let's go through the process again. 2k equals 168 over 3, take away 3 plus 1, which is equal to 168 over 3 minus 3 take plus 1 is equal to 54. So 2k equals 54. And k therefore will equal 27. So the first number is 27. The number of terms is 3. That works. So my answer, I've got a few more to try. So my answer is going to be n equals 3. And I also need to find the mean, which I haven't worked out yet, but I can go through that in a bit. This is the process that I need to go through, and I'm going to continue to do all sorts of these. So what I'm going to do is now start to just write them out, and you can follow what I'm doing. So if n is 4 next, 2k equals 168 over 4 minus 4 plus 1. That equals 165. That is odd. Therefore won't work. Give myself a bit more space, don't I, than that? So I'm going to say no, it doesn't work. Right, next, I'm not going to bother trying with n is 5. The reason being because it's not a factor of 168. There's no 5 as a prime factor, so let's go next one, which would be n is 6. Then we get 168 over 6 plus 1 over 6 minus 6 plus 1, which equals 23, which again is odd, so I'm not going to bother with that one. Next option, next prime factor, next option is 7, so let's try and draw a line under that. If n is 7, we've got 168 over 7 minus 7 plus 1, and that equals 18, which is even, and that means therefore, so sorry, that's 2k equals, isn't it? So therefore k equals 9, and it works. So this is one of my answers here. And I'll just put it straight down here. 3, 7. Let's try next one if n is 8. We get 2k equals 168 over 8. Take away 8 plus 1, which is 14. And so k is equal to 7 there. And so that works. So there's another one of my answers. 3, 7, and 8. I then went from there and I tried n is 12, 28, and 21. 12 didn't work. If n is 28, again didn't work. And finally, if n is 21, that didn't work as well. They all gave me odd numbers. So I've only got 3 answers here that work, 3, 7, and 8, and I need to work out the corresponding mean for each of those. To do that, I'm going to put it into my values for n and k into this thing to work it out, because that's what we said was our expression for the mean. And what that does is it gives us a mean of 28 to go with 3, a mean of 12 to go with 7, and a mean of 10.5 to go with 8. And there we are. So now, well, I've done all the work for this, write down all the possible sequences. Well, that is using what I just wrote down. So my mean was 28, and that was 3 numbers. So I can write out 28 in the middle. Obviously 3 numbers, I need 1 below and 1 above, with my mean of 12. That was with 7 numbers, so I'm going to do quite a few. 13, 14, 15, and 11, 10, and 9. And then the last one was a mean of 10.5, so I'm going to write out my 10 and my 11, and that was 8 numbers. N was 8, so I need 12, 13, 14, and 9, 8, 7. Now, this last one, I was unsure about how to approach this one as well, and I'm really looking closely at the time. But it says to find an even number bigger than 20 which cannot be written as a sum of consecutive integers. There must be an easy way of doing this. I simply tried a few, bit of trial and error, never hurts on a paper 6. You might arrive at an answer. I got some answers. They are the correct ones, which are 32, 64, and one which I didn't really bother to find, which was 128. There's certainly something to do with powers of 2 here, which I haven't seen a nice, easy route to get towards the answer. But this, again, remember, is just 1 mark for this part, this question 7. So just give it a go, try something out. I might it might dawn on me as I go through the next section, but I would say at this point, move on to the modelling. Okay, the revised spend, again, 45 minutes. This task looks at maximising the number of cars that can partially save a point on the road in an hour. Okay. Takes 1 second to react to an emergency when driving. Speed of a car is 54 kilometers per hour. Calculate the numbers in meters that travels in 1 second. So obviously this is, well, the first thing we should hopefully be identifying is it's all about units. We're talking about meters and seconds, whereas here we're kilometers and hours. So we need to make the conversion between them. So 54 kilometers per hour, we need to say, well, how many meters is that and how many seconds is that? So what we're going to have to do here is to multiply by 1,000 and divide by 3,600. So 54 times 1,000 is going to be 54,000. So that's how many meters there are in a kilometre. And divide by 3,600, which is how many seconds there are in an hour. And if you're unsure about that, you can just do 60 times 60. And that simplifies to 15 meters. Okay. Speed of the car is x. Show the number of meters A travelled is approximate in 1 second is 0.278. Okay, so we're going to have to go through the same process. X times 1,000 divided by 3,600, which is, let's just cancel those, 10 over 36 x, which if we put into our calculator is 0.278. X's. Okay, next we've got the speed of the car is x. When the driver brakes, the number of meters b that the car travels before stopping is k lots of x squared. Okay. When x is 50, b is 20. Okay, so this is just proportion. And we've even got that constant of proportionality written as k, just as we did in class. So that's quite nice. So we're saying the number of meters b that the car travels before stopping is equal to k lots of x squared. But in this instance, b is 20, x is 50, and so 20 over 2,500 is equal to k, or that simplifies to 1 over 125. So expressing for b in terms of x, b is equal to 1 over 125 x squared. Okay. Part 3. For safety, the distance between the cars travelling at x must be a plus b. That makes sense of the diagram that I'm looking at below. We've got this a section, we've got the b section, and the distance between them is a plus b. The average length of a car is 4, so the number of metres between corresponding points on the road is a plus b plus 4. So the corresponding point is the front of the car, a plus b plus 4 gets me to the front of the car as well. Okay. Explain why a model for the number of cars n safely passing point P in 1 hour is n equals 1,000x divided by 0.278x plus kx squared plus 4. Now this is a funny question in many ways, because it's just asking us to explain why. What I've written down is the number of cars is equal to the distance in 1 hour divided by the distance between corresponding points. So that is the distance over this a plus b plus 4. But if you look back, we've all got an expression for b, we've got an expression for a, which was the stopping distance, and you can see it all there and how it pieces together. So I might just write out, perhaps this is my communication, 1,000x, a which was 0.278x b, which we said was 1 over 125 x squared, or k x squared, just looking at how it wants it here, plus the 4. And that will tell us how many are going to pass through a specific point in that hour. Okay, part C. Use your value for k from question 2 to sketch the graph. Okay, so I'm just going to put this into my GDC. Let's just have a look at what we get. So all I'm doing here is I'm going to put exactly that function that I got in the previous one, previous part of the question, into my GDC, and it gives me this answer. Now I have also plotted the maximum point just through analysing graph, and all I need to do now is to just sketch that. So if I am able to move this out of the way, all I'm looking to do is get the right shape, and it's something like that. Now, looking at the coordinates, the maximum number of possible cars in 1 hour is in the y, represented by the y-axis, obviously n in this case, so that y-coordinate is 1572.9. Find correct one decimal place the speed, so that's going to be x-coordinate, so that's 22.4 if I round it, and that's in kilometers per hour. Comment on the size of this answer. Well, it's quite slow, isn't it? I might put slower than most speed limits. That's what I wrote down. Okay, now, can I move this out the way? Yep. When you increase the average length of a car, what is the effect on the maximum number of cars that can pass point P in 1 hour? So let's have a look back and identify what it is in here that relates to the length of the car. Well, it was defined on the previous page as that 4, which in the graph is this plus 4. So all I did to work this out was plugged in some different numbers. So I just changed the 4, because it says increasing, I changed the 4 here to a 10 just to see what happened, and generally what happened was it came up with, I haven't copied this graph, but it moved a little bit like this, I think. So the maximum number of cars, which is effectively that n, that's this maximum point now. It's obviously decreased, and because, so it's gone from, this y value down to here, and it's gone from this x value up to here. So the max speed at which this maximum is possible, well, that's actually increased. And that's how I used the graph in that to answer that page. Okay, so turning the page, we've now got a revised model for traffic flow, which does not include the braking distance B. This is because the car in front also travels the same braking distance, so the revised model uses k is equal to 0. This model also allows 2 seconds instead of 1 second for the driver to react to the car in front stopping quickly. Assume the average length of the car is 4 meters. So the process I went through here was to write out our original model, which was, n being equal to 1000x divided by 0.278x plus kx squared plus 4. Now, what changes have we made to that? This is no longer 0.278 because it's going to be 2 seconds instead of 1 second. So that was, how many 2 seconds are there in an hour? Okay, that's going to be now 1,000 divided by, instead of 3,600, it's going to be 1,800. That's going to be x's, which is now 0.556x to 3 significant figures. And the other thing that's happened is k is equal to 0, so that means I can just get rid of this. And it remains at 4, so that 4 is going to stay as it is, so that's fine. So n now will equal, if I tidy that up, now n's now going to equal 1,000x over 4 plus 0.556x. Okay, what does that look like? Well, let's find a picture of it on our GDC. Okay, so what I've chosen to do here is to plot it on top of the previous one. So you can see, hopefully, the blue one is my original graph. This is the new one, which is in black. So obviously we've got this thing here. So that's the shape that I'm going to draw now. So let's move this out of the way. And it's going to have to look like that. So it continues to rise. It probably should have been a bit... I don't feel that's steep enough at the start, so I'd probably just revise that a bit and go steeper and tailing off, but it's continuing to rise. Yeah, that's okay. Quite happy with that. And there we are. So what does it say next? Can 1,800 cars safely pass point P in 1 hour? Use algebra to explain your answer. So that's across the page. Let's go across there. Move this out of the way. I think I'm going to come back to that in a minute. I'll just put that in the corner here, so it's not going to bother us. So can 1,800 pass? Well, let's just see. The n would be 1,800. So in that case, it'd be 1,800 would be equal to my new formula, which is 1,000x over 4 plus 0.556 x's. So what have I got? I've got 1,800 multiplied by 4 plus 0.556x equals 1,000x, meaning I've then got, if I expand this, I've got, oh actually I can divide by 100 on both sides, might make life a little easier, which leaves me with 18 times 4 is not 10, it's 72, plus 10.008x, and that equals 10x. Now, that means I've got 72 is equal to minus 0.08x. And if I continue to solve this, I can see that x is going to be negative. So I can state from there that no, because x is negative. Cool, so I've shown that there's no value for x that will work. Obviously x is representative of the speed that they're going, and you can't have a negative speed. Oh no, oh no. Okay. There is one speed greater than 0 at which both models give the same answer for cars per hour. Find this speed. Let's bring this back. Analyze graph, intersection, go across the point, and here it is. All we need to do is read it. 34.75, 1490.1. So what I might do is just write down the coordinates there. Silly boy. 34.75 and 1490.1. Now all I need to do is identify or be sure that I know which one is the speed, and that should be my x coordinate. So it's at 34.75 kilometers per hour. And there we are. Jobs are good. So a really useful exercise to do is to just go back and look at where we could have perhaps got stuck and where we perhaps could have been able to continue as well. I think here is an opportunity, this question 4, for us to get in this revised formula, because we know we're just adapting the previous one which was given to us. So actually I think from here, particularly with the GDC work after this, all of these are worth marks that we can certainly pick up even if we didn't complete the question 3 in its entirety. Going back again, yeah, this is GDC work. So as long as your GDC work is accurate and links with what's been stated, then you're going to be picking up marks here. This formula was given to you, so again you can plug that into your GDC and ensure that you're getting that. Now it does matter. It matters what value you get for K, but if you've got a different value for K, there will be all sorts of follow-through marks, as long as what your value does matches up with your graph and it's all labelled absolutely correctly and spot on, then you're going to be picking up all those marks. So I felt the modelling here was okay. I think the investigation was a little bit more challenging, but again, that's personal preference. Again, let's look back in the other one where we could have perhaps picked it up. Well, there's nothing particularly elegant about this answer, but trial and error is always an option that you can go into, and just trying out numbers, I'd be interested to find out if there is a better way of approaching it. This is the way I managed to do it with so many variables. I needed to just try out some values for n. And don't be shy to do that. If you need to just try stuff out to try and arrive at an answer, then that's absolutely fine. And there we are. That's that one done. Oh no, hang on.